Good afternoon. So let's go over the concept of a Fourier sine series. And this time around, we're going to use the same concepts like the Fourier cosine series, and we'll move on with some of the parts a little bit faster because the idea is really the same, except we're going to focus primarily on what type of representation you get if you write it in terms of sine series. But the way to obtain it is very similar. And in fact, portions of the whole process is given in the portion of it is given in the homework, as I'll mention immediately. So the idea is the same as before. Let's say we have a function f of x which is piecewise continuous on the interval 0 pi. Again, we're going to start with this interval because it's the easiest one, but later on we're going to extend it to any interval. Piecewise continuous on interval 0 pi, and we say that f of x has a Fourier sine series on this interval if you can write f of x as a series of, as a linear combination, right, in a series of sine functions, a1 sine of x plus a2 sine of 2x dot dot dot, or if you write it in a summation, that summation from 1 to infinity of an sine of nx. Notice there is no non-zero constant term to begin with, because sine of 0 is 0, right? Unlike the cosine series when the first term was not 0, right? Unless it is 0 because of the function to deal with, but it can be non-zero. So that a naught over 2, the first term in the cosine series, was multiplied by cosine of 0x, which is 1 essentially. Here sine of 0x will be 0, so then you don't need any coefficient. So for the Fourier sine series, n is always 1 starting from 1, right? 1, 2, 3, and so on, not from 0. And the formula for the coefficients is very similar. The reason why you can obtain such representation is because just like cosine functions, as it turns out, these sine functions, sine of x, sine of 2x, sine of nx, are orthogonal on the interval 0 pi. This is a homework basically to you. Remember what that means. Orthogonal means that the integral from 0 to pi of the product of any two, sine of nx, sine of mx, is going to be 0 as long as m is not equal to n, and is equal to pi over 2 if m is equal to n. And like I said, let me actually check if I remember this. I think this was a homework. I want to make sure that is the case. Yes. Okay. So it's proved, I mean, we proved it before for cosine nx, cosine mx. And remember, because of this property, we are able, in fact, to compute the formula for the coefficients. You multiply each summation with one of these sine. You fix one of these sine of nx. And when you integrate over the integral 0 pi, all terms will be 0 except the one that gives you an. And as it turns out, like I said, the formula for the coefficient is very similar. An is 2 over pi, the integral from 0 to pi of f of x sine of nx dx. And just like the cosine series, we're going to use tables of series to obtain these representations. But for now, let's use the formula for a couple of examples. And we're going to compare with the cosine series. But before we do that, before we do a couple of examples, let's just emphasize once again that these representations are not just good for 0 pi. But because sine function is an even function, so sine of nx is, not even, is an odd function. Sine of, that means sine of minus nx is minus sine of nx. That means the Fourier sine series represents also the so-called odd extension of the function itself. So the starting function over the interval 0 pi can be extended to an odd function of the interval minus pi pi, and then you can extend that to a periodic function of period 2 pi. So basically you can get what is called the periodic odd extension as opposed to the periodic even extension. And let's put these two together so we can have them as an idea before we move on to examples. So you can start with the same function. In fact, let's do that side by side with two graphs. You can start with the same function. Let's say it looks like that, just to have a nice easy shape between 0 and pi. And like I said, the same function here. Right, so in both cases, the seed, so to speak, is the same function. I'm going to make it thicker a little bit so we can see it clearly here. So in both cases, we have y equals f of x. Same thing here, y equals f of x. The Fourier cosine series for this function will represent obviously the function itself on the interval 0 pi, but also the even extension. That means the same shape reflected over the y-axis. So that means you have now a function between minus pi and pi. And of course, the periodic extension over this, right? Because the function is period with period 2 pi. So this is what the Fourier cosine series for this function will represent, again starting with the function in the interval 0 pi. On the flip side, if for the same function we compute the Fourier sine series, because that series is odd, because the sine function is odd, it will also represent the so-called odd extension. Now remember, the odd functions are symmetric with respect to the origin. So you can extend this function to an odd function by reflecting the graph over the y and then over the x-axis. In other words, if you sketch the symmetric part with respect to the origin. So again, remember the seed, the original function is the same on the interval 0 pi, but the sine series will represent the odd extension. And of course, then this can be extended throughout the real axis line, because again, the sine function is also a period with period 2 pi. So it's important to understand that although cosine series, sine series for the same function will obviously represent the same function in the interval 0 pi, if we extend them to an even or odd extensions, then of course that'll be a different shape altogether. And as I said before, we need both depending on the context of the problem. So with that in mind, let's move on to the second page with a couple of examples. All right, so let's do this example, that the same function as before, our first example. So let's say I want the function f of x equals x with x between 0 and pi, and I want to write it as a sine Fourier series. Which means I need to compute the integral, I need to compute 2 over pi, the integral from 0 to pi of that function times sine of nx dx. And the function is x. So this calls for the integration by parts method. Remember, n is 1, 2, 3, and so on. And let's see, to do it by parts, we want to write sine of nx as a derivative. The antiderivative of sine is minus cosine. So that's going to be minus cosine nx over n. And then by parts, that's going to be minus x over n cosine of nx between 0 and pi, minus the integral from 0 to pi, x prime, which is 1, times minus cosine nx over n. So 2 over pi, and let's plug in pi for x, so it's minus pi over n cosine of n pi, minus 0, because it's going to be 0 over n, so that's it. Minus with minus becomes plus. We can maybe move 1 over n outside, and we just have to integrate cosine of nx dx. Now notice I don't have to worry about exceptions here. I divided by n, but because n is not 0, because it starts from 1, I don't have to take any case separately. So let's finish up that integral. The integral of cosine of nx will be sine of nx over n. And at this point, you've seen this before, you should realize this is 0, right? The second term. Because sine of n pi is 0, sine of 0 is 0. So basically you're left with minus 2 over n cosine of n pi. And let's see, I want to check also with the table, because I have to comment again on how this looks like if you look at the table. So let's leave it like that, and you can write then your answer that x is equal to summation from 1 to infinity minus 2 over n cosine of n pi, that's the coefficient, sine of nx. And it's perfectly fine to leave it like that. I'm perfectly happy with this format. But again, in the various, let's see, cosine of n pi, it's minus 1 to the n. Oh, yeah, I was looking at the wrong, yeah, that's fine. I was looking at the wrong table, and and I took a moment to actually realize that I was looking at the wrong table, and I got confused with the answer. So cosine of n pi is minus 1 to the n. So actually, yeah, I mean, in this case you can write it as minus 1 to the n. I mean, you can leave it like that, or with the minus 1 to the n, that's fine. It's still, either way is fine. So cosine of n pi cycles through between 1 and minus 1. Okay, so cosine of 0 is going to be 1. Cosine of pi will be minus 1. Cosine of 2 pi is equal to 1, and so on. So when n is even, you're going to get 1. When n is odd, it's going to be minus 1. So cosine of n pi is basically minus 1 to the n. You got to pay attention basically to see whether minus 1 or 1 associates to n even or odd, basically. Because that means if it cycles through between minus 1 and 1, often it depends on whether it starts with 1 or not. Because n starts with 1 and 1 is odd, then it's minus 1 to the first, which is minus, and then minus 1, 1, minus 1, 1, and so on and so forth. So this cosine of n pi can be replaced by minus 1 to the n. And now it's fine to combine the extra minus, right? There's no reason to leave it outside, this extra minus. So minus 1 times minus 1 to the n can be written as minus 1 to the n plus 1 over n sine of nx. And in most of the tables, you will see the answer for x as a Fourier sine series in this compact form, minus 1 to the n plus 1 over n sine of nx. And again, if you want to represent the graph, what actually this type of series covers, and just like before, like in the previous page, let's actually write side by side the Fourier sine series and the Fourier cosine series, right? So for the same function, for the function x, if it was Fourier cosine series, that was minus pi over 2 plus 2 over pi summation from 1 to infinity, what was it, minus 1 to the n minus 1 over n squared cosine of nx. So that was the Fourier cosine series. In the interval 0 pi, again, both functions will represent the same thing, namely the function f of x equals x. So far so good. I mean, in this case, it's just the same function, but represented using different functions. In one case, sine functions, and the other one, cosine functions. On the other hand, the first one, the Fourier sine series, also covers or represents the odd extension of this. Odd extension means that half reflected over the origin, so that you have now a function between minus pi and pi, and of course the periodic extension. This will be 3 pi, for example. The cosine series for the same function will also represent the even extension, which means the reflection of that semi-half, right? That half, right half of the interval. And then, of course, the periodic extension. So they represent different functions outside the interval 0 pi, right? So the starting function is the same in both cases. So I'm going to make one remark here, and we will talk about that in more details later. Notice that if you have either a Fourier sine series or a Fourier cosine series, that's basically good for either odd functions or even functions. So stands the reason, what would you do if you need, for example, a Fourier series for a function which is neither odd nor even? And that will lead to the more general Fourier series, which is basically a combination of sine and cosines. But we'll get to that in a later lesson. For now, I want to do one more or two quick examples and more comments, and then that's it for today. So just one more page, stay tuned for it. So let's do by formula the Fourier sine series for the constant function 1, just like before in the previous lesson. Constant function 1 between 0 and pi, but this time I want the sine series. So according to the formula, of course, an is going to be, so we want f of x, or 1, summation from 1 to infinity an sine of nx. And then an will be again 2 over pi, the integral from 0 to pi, 1 times sine of nx. And again, n is 1, 2, 3, and so on. Now, this integral, the integral is minus cosine. So 2 over pi minus cosine of nx over n between 0 and pi. And if I plug in pi, let's see, I have minus 2 over n pi cosine of n pi. Then it's going to be minus, put parentheses here, minus 2 over n pi cosine of 0. Gotta be careful with that double negative. So we have 2 over n pi, because cosine of 0 is 0, minus 2 over n pi cosine of n pi. Now remember from the previous example that cosine of n pi can be written as minus 1 to the n. So an is 2 over n pi 1 minus 1 to the n. So that means 1 as a Fourier sine series can be written as summation from 1 to infinity 2 over n pi 1 minus negative 1 to the n sine of nx. So you can again leave the answer like that. Again, I want to warn you that in many problems, they will cycle through to the non-zero terms only, which is again more pain than necessary basically. But just because you will see this type of format of the answer, I'm going to write it down again here. Notice if n is even, 1 minus negative 1 to the n becomes 1 minus 1, which is 0. Which means instead of cycling through all numbers, we can replace n with 2n minus 1 so that we can force the summation to be through the odd coefficients only. So 2 over 2n minus 1 pi, 1 minus negative 1 to the, so 1 minus minus 1 to the n becomes 1 plus 1, which is 2, right? Because minus 1 to the n is minus 1 if it's odd. So there's an extra 2 here, and then sine of 2n minus 1x. So basically another version, and this 2 times 2 over pi becomes 4 over pi. In some tables, you'll see the Fourier cosine series for 1 written like this. So that is another version. Which again, I don't like. You will see immediately the reason why. Because, for example, let's say I want to come up with a combination of function which is not in the table. So let's say I want pi minus x as a Fourier sine series. Now remember that in the previous page we established that x as a Fourier sine series was summation from 1 to infinity 2 times minus 1 to the n plus 1 over n sine of nx. And so suppose the question is to find a sine series for the function f of x equals pi minus x on the same interval 0 pi. So this is the problem here, because we could actually combine this. We could think of this function as pi times 1 minus x. So that means I could throw in the function, the series for 1 and the series for x there. But then it will be difficult to combine them if one of them goes through the odd numbers only and the other one through all the integers, 1, 2, 3, and so on. You have to have some, in order to combine the summations, you need to have basically the same numbers, I mean the same indexes for n, same values for n, in this case 1, 2, 3, and so on. So that means I'm going to prefer this format, and then of course the one obtained for x previously, right? So pi minus x is pi times the series for 1 minus the series for x. So we have pi times the summation 2 over n pi 1 minus negative 1 to the n sine of nx, and then minus the summation for x and let's put everything inside the summation and pull out sine of x. So first of all, notice that I can bring pi inside the summation here. So I have 2 pi over n pi quantity 1 minus minus 1 to the n, from which I subtract minus 2 over n minus 1 to the n plus 1 sine of nx. You can leave it like that, although if you actually pay close attention, this actually can be simplified further without too much effort, because pi cancels over here. And pay attention here, when I distribute 2 over n, I get 2 over n And then this minus 1 to the n, I can make it plus minus 1 to the n plus 1. So I can combine minus 1 with minus 1 to the n. So it'll be plus actually 2 over n minus 1 to the n plus 1. And then minus 2 over n minus 1 to the n plus 1. So this tedious term cancels, and then you're done, and you say that pi minus x is summation from 1 to infinity 2 over n sine of nx. That's actually one of the easiest series in terms of its coefficients. Now you remember that in the cosine series for 1, right, so when f of x equals 1, we had a trivial cosine series. So that was not a surprise, because if you start with 1 between 0 and pi, the even extension and then the periodic even extension just keeps on giving you the constant function 1. So that was not a surprise. Also, as another point to be made, I mean, basically a constant is essentially the first term in the cosine series. So when the function is a constant everywhere, the Fourier cosine series essentially is trivial. So that was for the cosine series. But for the Fourier sine series, as the answer indicates here, right, as you will see here on the top of the page, it's not trivial, right? And again, that's not surprise, because if you start with 1, constant function 1, between 0 and pi, the odd extension flips this shape over the interval, over the origin, so you get basically this shape. It's basically between minus pi and pi, you get this discontinuous function, right, between these two pieces. It's not constant anymore over the interval minus pi. It's only constant over each half interval, but the constants are not the same, right? It's going to be minus 1 between minus pi and 0. And of course, when you do the periodic extension, you basically obtain this discontinuous function. So it's not a surprise that the Fourier sine series in this case is not trivial. So at this point, the next lesson will be a demonstration of how these series converge to these functions as you plot more and more terms. And that's it for today.